So imagine you want to send a message across London,
Right.
but it's the year 1843.
Okay, 1843, no smartphones.
Right. Absolutely zero screens. If you wanted to use the absolute most cutting-edge, mind-bending technology on planet Earth, you had to physically walk into a room and stand in front of this machine. And it looked like a bizarre wooden grandfather clock.
But not for telling time, I assume.
No, not at all. Instead of a clock face, it had this grid of letters. And mounted in the middle of it were 5 magnetic needles.
5 needles, like compass needles.
Yeah, exactly like that. And to send your message, a technician miles away essentially wiggled magnets, which made those specific needles twitch. And they would point to, like, the letter A.
That sounds incredibly tedious.
It was so clunky. I mean, it was this massive physical thing. But the crazy part is it completely shattered the absolute physical speed limit of human knowledge. So welcome to the deep dive.
Today, we are exploring a really remarkable stack of historical engineering texts, right?
Mm-hmm.
And these technical chronicles.
Yeah, and they paint a picture of a world that is just, honestly, it's really hard for us to even conceptualize now.
It really is.
Huh?
Because, I mean, for thousands of years, across every single empire and civilization, information was quite literally tied to the speed of muscle and wind.
Right, like a horse or a boat.
Exactly. A declaration of war or, the price of wheat in a neighboring country or just a letter from your family. That news could only travel exactly as fast as a horse could gallop, or as fast as a wooden ship could sail across the ocean.
Which is just wild to think about. That is the baseline we're starting from today. Our mission for this deep dive is to zoom in on one very specific revolutionary chapter in these engineering texts.
We're talking about the early electrical telegraph experiments.
Yes. We are going to unpack exactly how humanity figured out the physical mechanics of translating human thought into invisible electrical energy.
Which was not an easy process. It involved wild parlor tricks and some really serendipitous scientific accidents.
Oh, and the fierce transatlantic rivalries, we can't forget those. They birthed the very first digital network. So if you are listening to this on a smartphone right now and it's constantly buzzing with notifications, you are about to find out exactly who to blame for that anxiety.
Yeah, you can blame frog legs, compass needles, and a frustrated portrait painter who decided to basically rewrite the laws of physics.
It's such a weird cast of characters because we so often view the digital age as something that began with, like, enormous room-sized vacuum tube computers.
Right, we think of the mid-20th century.
Yeah.
The 1940s and 50s,
Oh.
Alan Turing, stuff like that.
Exactly. But diving into these sources reveals that the true digital revolution, the conceptual realization that human language could be abstracted into discrete binary pulses and fired across the globe, that actually happened much earlier.
Decades earlier, in the 1830s and 40s.
But before anyone could even dream of building a telegraph, the scientific community had to actually understand the raw material they were trying to tame, right? They needed to understand electricity.
Yeah, and reading through these 18th century accounts, they definitely weren't treating electricity like a communication tool yet.
Not at all. They were treating it like a magic show. It was pure spectacle.
Totally. It was theater for the aristocracy. In the late 18th and early 19th centuries, scientists knew electricity existed, but they conceptualized it as this untamable, almost mystical force.
Right. Which brings us to Luigi Galvani.
Yes. Galvani, in the 1790s, he was an Italian physician and an anatomist, and he famously experimented with the dissected legs of frogs.
Which I just have to say is so incredibly macabre.
It is, yeah. So he discovered that if you applied a spark of static electricity to the exposed sciatic nerve of a dead frog, the muscles would violently contract. They would literally twitch and kick.
I was reading that section and just thinking about how gross that is, but also it is the perfect visceral visualization of invisible energy transferring into physical action.
Right, you're taking a dead thing and making it kick, which is exactly why it just completely captured the public imagination.
Oh, it deeply influenced the cultural zeitgeist. I mean, Mary Shelley's Frankenstein is a direct descendant of Galvani's frog experiments.
Exactly. People were terrified and fascinated. Galvani theorized that he had discovered what he called animal electricity.
Like it was inside the frog itself?
Yeah, he believed it was an inherent life force, like a fluid that was native to biological tissue. But his contemporary, another Italian physicist named Alessandro Volta, he looked at that exact same experiment and came to a radically different conclusion.
And a vastly more important one, right?
Oh, absolutely. Volta argued that the frog was just the conductor, not the source of the power.
The frog was just the meat in the sandwich.
That's a great way to put it, yeah. He argued it was actually the contact between the two different types of metal that Galvani was using in his dissecting instrument.
Oh, so the scalpel and the hooks or whatever.
Right. Those metals were interacting with the moisture in the frog's flesh, and that is what created the electrical current. So to prove this, Volta completely removed the biological element.
No more frogs.
No more frogs. Around 1800, he invented the voltaic pile. He basically stacked alternating discs of zinc and copper, and he separated each pair with a piece of cloth or cardboard soaked in salt water.
Which gave us the very first true battery.
Yes, exactly.
But I want to pause here, because understanding why the battery matters so much means we have to understand why the stuff that came before it was so incredibly useless for communication.
Right, the static electricity attempts.
Yeah, the sources mention a Spanish inventor named Francisco de Salva. In 1795, so 5 years before Volta's battery, Salva proposed an electric telegraph.
But his power source was a Leyden jar, right?
Exactly. He wanted to use static electricity from a Leyden jar to charge a pithball electroscope.
You might need to explain what a pithball is.
Oh, yeah. So for those listening, a pithball is just a tiny, incredibly light ball of plant matter hanging on a string. And when you charge it with static electricity, it physically repels away from other charged objects.
Okay, so you wanted to use a repelling motion to signal letters.
Yeah. But using that to send a message sounds like trying to send an urgent text message, using only the static charge you get from rubbing a balloon on a wool sweater.
The balloon analogy is highly accurate, actually, when you look at the physics of it. Salva's idea was imaginative, sure, but it was just a mechanical and physical nightmare.
Because it's static.
Right. Static electricity, which is what they were storing in those early Leyden jars, is static. It's a surface charge.
Yeah.
It wants to discharge all at once, almost instantaneously, in just a single chaotic spark.
You can't control it.
Exactly. Plus, you cannot easily send it down a long wire because it constantly leaks into the surrounding air.
Oh, wait, really? It just floats away?
Pretty much. If the ambient humidity in the room goes up, your static charge just dissipates into the water vapor in the air.
So you string a wire 10 miles down the road, you charge it with static, and by the time it gets a mile out, the damp morning fog has completely eaten your message.
Yep, your signal is completely gone. You cannot sustain a controlled, modulated signal over a long distance with static discharge. And that is why Volta's invention in 1800 is the critical baseline.
Because the voltaic pile provided a portable, reliable, and most importantly, continuous source of electrical current.
It wasn't a sudden spark. It was a steady, flowing river of electrons.
Okay, but this brings up a massive historical gap that I honestly struggled with while reading the timeline in these texts.
The 40-year gap.
Yes. Thomas Jefferson is the U.S. president in 1800. We have the battery. We have a steady, reliable river of electrical power. Why did it take nearly 40 years to get a working telegraph?
It's a great question.
Right. Like, if I have a battery in 1800, why am I waiting until the Victorian era to actually send a message? What were they missing?
So the delay really comes down to the profound difference between generating power and controlling that power at a distance to do meaningful work.
Okay, elaborate on that.
Having a voltaic pile means you can successfully push an electrical current down, say, 10 miles of copper wire. But consider what happens at the destination. The current reaches the end of the wire, and then what?
It just sits there, or it runs into the ground.
Exactly. It does nothing that a human being can perceive. Early scientists lacked the physical mechanism to make that electrical current translate back into kinetic energy.
Into motion, into something readable.
Right. You can send a continuous current 100 miles, but if it just hits a dead end, it is entirely useless for communication. The transduction mechanism, the actual way to convert electrical energy back into physical movement, was completely absent from human knowledge.
And according to the historical chronicles, the answer to this massive engineering bottleneck came entirely by accident.
Yes, during a physics lecture.
In Denmark. I love this moment so much because it fundamentally changes how we understand the entire architecture of the universe. And it is the master key that unlocked the telegraph.
We are talking about Hans Christian Ørsted in the year 1820. Ørsted was a Danish physicist, and he was giving a lecture to his students, basically demonstrating the heating effects of a continuous current from a voltaic battery passing through a wire.
Just a standard classroom demo?
Exactly. But by sheer unadulterated chance, there happened to be a magnetic compass sitting on his laboratory workbench. and it was positioned right underneath the wire he was using for the demonstration.
The ultimate right place, right time scenario in the history of science.
It really is. So when Ørsted connected the circuit and the electric current began flowing through the wire, he noticed something out of the corner of his eye. The compass needle, which was previously pointing north, suddenly deflected.
It twitched.
It twitched, and it aligned itself perpendicularly to the wire. And then when he disconnected the battery, the needle swung right back to north.
To a modern listener, this needle twitching near a wire might seem like a really small, almost trivial observation.
Sure, because we learn about electromagnets in grade school now.
Right. But we have to put ourselves in the mindset of an 1820s physicist. At that time, electricity and magnetism were considered two completely separate, entirely unrelated forces of nature.
Like gravity and light.
Exactly. The idea that one could influence the other was bordering on heresy.
It was an absolute paradigm shift.
Mm.
Ørsted's serendipitous observation provided the very first empirical proof that an electric current flowing through a conductor actively generates a magnetic field in the space around it.
The birth of electromagnetism.
Yes.
Yeah.
And the scientific community just exploded into action.
Mm.
Almost immediately, you have the French mathematician André-Marie Ampère. He took Ørsted's practical observation and applied a rigorous mathematical framework to it.
Right, Ampere's law.
Exactly. Proving mathematically that electric currents produce magnetic fields that can exert physical forces on other currents and magnets.
But the real MVP for the telegraph in this specific era seems to be an English engineer named William Sturgeon. This is a few years later, in 1825. He takes this theoretical physics and actually turns it into a tool.
Sturgeon invents the first practical electromagnet, and his design is brilliant in its simplicity. He took a piece of soft iron, shaped like a horseshoe.
Okay.
He varnished the iron so it was electrically insulated, and then he wrapped bare copper wire tightly around the horseshoe in a coil.
I want to clarify the varnish part for the listener, because if you don't insulate the iron, the electricity will just take the path of least resistance, right?
Oh, absolutely. It would just shoot straight across the iron block instead of traveling the long way around through all the coils of the wire.
That makes sense.
It is a crucial distinction. The current must be forced to travel through the coil to generate the cumulative magnetic field. So when Sturgeon sent a current from a battery through that coiled wire, the iron horseshoe became an incredibly powerful magnet.
Like how powerful?
It was capable of lifting 9 pounds of iron, which was just astonishing at the time for a device of its size. But the most vital characteristic of Sturgeon's invention was not its physical strength. It was its temporary nature.
Because he used soft iron instead of, like, hard steel.
Yes. When he disconnected the battery, breaking the circuit, the magnetic field collapsed, and the magnetism in the iron vanished almost instantly.
I am putting myself in the shoes of a 19th century engineer looking at this horseshoe. Ørsted and Sturgeon didn't just prove force at a distance, they proved controllable force at a distance.
Exactly. Controllable is the key word.
With an electromagnet, you could sit in one room, close a circuit with your finger, and cause a heavy piece of metal to physically move in another room miles away. And you could turn that magnetic pole on and off at will.
The significance of that on and off capability just cannot be overstated. This binary state, magnetism present, magnetism absent, is the absolute bedrock of encoding information.
It's binary, ones and zeros.
Yes. Everything we do in the digital age, every single email, every podcast audio file you listen to, it is all built on the foundation of binary states. Sturgeon proved it could be done with just iron and wire.
It is staggering to conceptualize. The very first communication networks were basically just highly coordinated, long-distance compass twitches.
That's literally what they were.
You are just wiggling a magnet from 30 miles away. And once that theoretical barrier was demolished, the engineering texts show that the race was officially on to build a practical commercial device.
And it immediately became a fierce international rivalry. Engineers in Europe and America took two drastically different philosophical approaches to the problem.
Right, how to translate the complexity of human language into these simple electrical twitches.
Exactly.
Let's start with the British approach, because honestly, it feels like the most logical first step if you are trying to invent a machine that talks. We have Sir Charles Wheatstone and Sir William Fothergill Cooke. They patent their telegraph system in 1837.
Yeah, Cooke and Wheatstone built what is known historically as the needle telegraph.
Hmm.
Their approach to engineering this network was highly literal.
They wanted to spell it out.
They wanted to replicate the written alphabet as directly as possible, so they constructed a device with a diamond-shaped dial face. On this dial was a grid of the entire alphabet. And mounted in the center of the dial were 5 magnetic needles, each one controlled by its own dedicated electromagnet hidden behind the face.
So imagine looking at a clock face, but instead of 2 hands, there are 5 needles just pointing straight up and down.
Right. And to send a message, the operator pressed a series of buttons on a keyboard. This keyboard would send electrical current down 2 of the 5 transmission wires simultaneously.
2 at a time.
Yes, 2 at a time. At the receiving station miles away, the incoming current would energize 2 specific electromagnets, causing 2 of the 5 needles on the dial to deflect at an angle.
Oh, I see where this is going.
If you trace the invisible lines extending from those 2 deflected needles, they would intersect directly over a specific letter painted on the grid.
That is so clever. They actually laid the first commercial line using the system between Paddington and Slough in London in 1843. And I have to admit, reading the description of this device, I find myself deeply sympathetic to the British approach.
Why is that?
It just sounds immensely better for the everyday user. You do not have to learn some arcane, complex code. You just look at the dial, watch the needles twitch, and read the letters they point to. It is highly intuitive. It's like a magical Ouija board.
From a pure user experience perspective, you're right. The Cooke-Wheatstone dial was remarkably intuitive. Any literate person could look at it and decipher the message with minimal training.
Right. So why didn't it take over the world?
Well, the Engineering Chronicles dedicate a lot of space to the fatal flaw of the 5-needle system. You have to analyze it through the brutal lens of physical infrastructure and economics.
Walk me through the physics of the failure. Why didn't this become the global standard?
To make that elegant 5-needle dial function, the physical requirement was just staggering. You had to string 5 separate continuous copper wires across the countryside.
Which means 5 times the copper.
5 times the copper, which was incredibly expensive. But even worse was the insulation.
Oh, because they're outdoors.
Yeah. Properly insulating overhead or underground wires in the 1830s was an absolute nightmare. They were experimenting with cotton wrapped in tar, or like burying wires in glass tubes.
That sounds incredibly fragile.
It was. If a heavy storm brings down a tree branch and snaps just one of those 5 wires, your entire permutational alphabet grid is ruined. The system is dead.
Because you suddenly lose access to all the letter combinations that required that specific wire.
Exactly.
Huh.
Furthermore, maintaining uniform electrical strength across 5 parallel lines simultaneously over long distances is highly problematic.
Because of resistance?
Yes. Electrical current degrades over distance. If one wire encounters more resistance due to a poor splice or maybe moisture getting into the tar, its needle might not deflect fully.
Oh, so it would point to the wrong intersection.
It would point to the wrong letter entirely. So the British system was conceptually beautiful, but inherently fragile and just prohibitively expensive to scale across a massive continent.
Meanwhile, across the Atlantic, we have the American approach, led by Samuel Morse and his mechanic partner, Alfred Vail.
Right.
The sources detail how Morse, who was actually a prominent portrait painter, got inspired during a transatlantic voyage on a ship called the Sully in 1832.
He was a painter, yeah, not an engineer.
Right. He was just listening to passengers discuss electromagnetism, and he became completely obsessed. Morse and Vail pursued an entirely different philosophy. The text refers to it as the single-wire imperative.
Just one circuit.
A single wire, rapidly opened and closed.
Morse and Vail looked at the infrastructure bottleneck and realized a profound philosophical truth about network design. They understood that you should not build a highly complex, fragile, and expensive physical machine just to mimic the ease of human writing.
You should do the exact opposite.
Exactly. You abstract human language to fit the absolute simplest, cheapest, most durable physical machine possible.
It's a single wire.
A single wire carrying a single intermittent electrical circuit. If a tree branch falls, you only have to repair one wire. The physical layer of the network becomes incredibly cheap and robust.
I was struck by what a massive conceptual leap that is. It is the leap from mechanical replication, like the pointing needles, to digital abstraction.
It's the core of modern computing, really.
They decided the physical hardware needed to be as dumb as possible, which meant all the complexity, all the intelligence of the system had to be shifted into the symbolic domain. Because they reduced the hardware to just one wire that can only be on or off, they literally had to invent a brand new language to bridge the gap.
And that brings us into the realm of the hardware and the code itself, which is rightfully viewed as an early triumph of what we now call information theory.
So how did the hardware actually work?
Well, the hardware they developed was incredibly elegant in its reductionism. The transmitter, which they called the key, was quite literally just a spring-loaded switch.
Just a button, basically.
Yeah, the operator presses the brass lever down, two metal contacts touch, the circuit closes, and the battery's current flows into the wire. The operator lets go, the spring pulls the lever up, the circuit breaks, and the current stops instantly.
It is just a rhythmic gateway for electrons. And the receiver at the other end?
The receiver utilized the groundbreaking work of Joseph Henry, an American scientist who had perfected the design of high-intensity electromagnets. At the receiving station, the incoming electrical current energized an electromagnet.
Okay, so a magnet turns on.
Right. And placed just millimeters above this magnet was a metallic lever called an armature. Originally, Morse and Vail attached a little steel stylus or pen to this armature. Beneath the stylus, they had a clockwork mechanism slowly pulling a continuous strip of paper tape.
So the paper is always moving.
Always moving. When the operator at the sending station held the key down, the current flowed, the receiving electromagnet turned on, and it physically pulled the armature down.
And the pen hits the paper.
The stylus pressed into the moving paper tape, embossing a mark. When the sending operator released the key, the magnet turned off, a spring yanked the stylus back up, and it left a blank, unmarked space on the moving paper.
It is brilliant, but I mean, dropping a stylus onto moving paper doesn't give you the alphabet. It just gives you lines of varying lengths.
Exactly.
And this is where Alfred Vail's contribution becomes absolutely fascinating to me. They have to map the 26 letters of the English alphabet plus numbers and punctuation onto these short and long electrical pulses, what we now know as the dots and dashes.
They could have just assigned these codes randomly or alphabetically. Like A is 1 dot, B is 2 dots, C is 3 dots, and so on.
That would be the logical way to do it.
But they didn't. Vail approached the creation of this language with rigorous statistical analysis. He actually visited a local newspaper printing office in Morristown, New Jersey, near where they were conducting their experiments.
I love this anecdote in the historical texts. Imagine this guy walking into a noisy, ink-stained 19th century print shop to solve a mathematical problem for an invisible network.
Vail goes into the printing office and observes the compositors. He looks at their typecases, the large wooden trays divided into small compartments where the printers kept the individual metal letters used to set the printing press.
Okay, what is he looking for?
Vail simply counted the quantities of each letter in the different compartments of the trays. He reasoned, quite correctly, that the printers knew exactly which letters were used most frequently in the English language, and they stocked their trays accordingly.
I was reading this and I immediately thought, this is the 19th century invention of data compression.
Oh, absolutely.
This is Vail inventing the .zip file. He is looking at the system and thinking, the letters we use the most often are going to be sent the most often. They should take the least amount of time to tap out.
Right, to save bandwidth.
Yeah, we need to save the operator's wrist from fatigue, and we need to free up the expensive telegraph line to push more messages through per hour.
It is the exact definition of statistical compression, anticipating the work of Claude Shannon by a century. By analyzing the printer's type cases, Vail confirmed that the letter E is the most commonly used letter in the English language.
So E gets the simplest code.
Exactly. He assigned E the absolute shortest possible symbol in their new code, a single brief dot. The letter T, the second most common letter, was assigned a single dash.
And the rare letters get the complex codes.
Precisely. Letters like Q, Z, or J were assigned much longer, more complex sequences of multiple dots and dashes because they would rarely bottleneck the network.
That makes perfect sense.
But there is a crucial element of Morse code that often gets overlooked in popular culture. We tend to focus on the dots and dashes, the positive presence of the mark. But the spaces, the silence between the marks, were just as mathematically important to making the system function.
Let's dig into that, because reading about the temporal rules of the code was a massive light bulb moment for me. Morse and Vail didn't just invent a code, they invented a strict temporal grid.
Yes, they established rigid rules based on time. They defined a standard baseline unit of time, the duration of one single dot. Let's say, for example, that unit is 1/10 of a second.
Okay.
A dash was strictly defined as being exactly 3 units of time long. So 3/10 of a second.
A dash is always 3 times the length of a dot.
Always.
Okay.
But then they defined the spaces. The silence between a dot and a dash within a single letter was exactly 1 unit of time. The silent space between entire letters was 3 units of time, and the space separating separate words was 7 units of time.
I want to challenge this from the perspective of an operator. Why be so rigidly mathematical about the silent spaces? If I'm tapping out a message, why does it matter if my pause is 3 units or 4 units? The letters are the letters.
The rigid timing of the silence is the secret to self-synchronization.
Self-synchronization.
Yeah. Imagine you and I are on opposite ends of a telegraph line. You are an expert operator, and you are tapping out a message incredibly fast. Your baseline dot might be a tiny fraction of a second. I am a beginner, and my tapping is very slow. My dot might be a full half-second long.
So our hardware is sending pulses at completely different speeds.
Yes, but because the code is entirely proportional, it doesn't matter. As long as your dashes are exactly 3 times as long as your specific dots, and your spaces scale proportionally to your speed, I can listen to your rhythm, lock onto your personal baseline speed within the first few letters, and decode the message perfectly.
Oh, wow. That is incredibly elegant.
It was the genesis of data serialization. It proved that you could take unstructured human thought, quantize it into strict, proportional temporal patterns, and perfectly reconstruct it on the other side of a wire.
And reconstruct it they did. The history books all point to May 24th, 1844. Morse and Vail finally secure government funding, and they prove the system works with the famous "What have God wrought" message.
Right from the bottom.
They sent it 40 miles, from the Supreme Court chamber in Washington, D.C., to a railroad station in Baltimore. It is a massive triumph. But, as these engineering sources detail, connecting a 40-mile test track is one thing. Connecting an entire sprawling continent requires defeating a silent, invisible enemy that constantly stalks the network.
Electrical resistance.
Right. The tyranny of distance.
The fundamental physics of electromagnetism presented a massive, seemingly insurmountable barrier to a national network. As an electrical pulse travels along miles of iron or copper wire, it suffers from a phenomenon engineers call signal attenuation.
Break down attenuation for the listener. What is actually happening to the electricity in the wire?
Well, the wire itself, no matter how pure the metal,
Mm-hmm.
has natural electrical resistance. As the electrons flow, they bump into the atoms of the copper or iron, generating microscopic friction.
And friction creates heat.
Exactly. That friction releases energy as heat. So the electrical pulse is constantly bleeding energy as it travels. Furthermore, the wire running alongside the Earth acts somewhat like a giant, inefficient capacitor, leaking tiny amounts of energy into the surrounding environment.
The signal is quite literally running out of gas.
The sharp, powerful square edges of the binary pulse that left the transmitter begin to round off, flatten out, and weaken. Beyond a few tens of miles, the electrical signal would become so incredibly weak that when it finally reached the receiving station, it couldn't generate enough magnetic force in the electromagnet to physically pull down that heavy metal armature.
The stylus wouldn't drop.
Nope. The message would just fade into complete silence.
Looking at this problem, the obvious brute force solution seems simple to me. If the signal is too weak when it arrives, just start with a much stronger signal.
Just turn up the juice.
Yeah. Hook up a gigantic, massive battery at the sending station and blast the current down the line so hard that it survives the trip. Why didn't they just do that?
Because of the thermal limits of the physical hardware. If you attach a massive high-voltage battery to the sending key, the moment the operator presses that brass lever down, the sheer volume of current rushing across the tiny contact points would create an arc flash.
Oh, like a mini lightning bolt.
Yeah, you would weld the key shut, or you would physically melt the thin copper wire in the receiving electromagnet. You cannot force 1,000 gallons of water through a garden hose just because you want it to shoot further. It'll burst.
So they're trapped. They can't increase the power and they can't stop the resistance. How did they solve it?
The solution was an ingenious device called the telegraphic relay, which Samuel Morse actually conceptualized early on, around 1837, though it took time to perfect. In the context of the digital age, the relay is arguably the most important unsung hero of modern technology.
Okay, I really want to visualize this. Walk us through the step-by-step mechanical action of a relay.
Imagine an electrical signal has just traveled 50 miles from city A to city B. It is exhausted, it's attenuated, and it's incredibly weak.
Barely a whisper.
Right. Instead of trying to use that dying signal to operate a heavy, stiff stylus to print onto paper tape, you route that weak signal into the relay. The relay is a highly sensitive, miniaturized electromagnet. It is wrapped in thousands of turns of very fine wire so that even the faintest whisper of an electrical current will magnetize it.
So it requires Almost no energy to turn on.
Exactly. And the metallic armature sitting above this tiny electromagnet is feather-light. It only needs to move a fraction of an inch. So the dying 50-mile signal arrives. It energizes the sensitive relay coil just enough to pull down that tiny feather-light armature.
And what does pulling down that little armature accomplish?
This is the genius part. That tiny armature is a switch for an entirely separate local electrical circuit. Sitting right next to the relay is a fresh, powerful battery that is not connected to the first 50 miles of wire at all.
Wait.
When the weak signal pulls the armature down, two metallic contacts touch, which closes this new local circuit.
Oh, wow. I see it now.
The dying signal uses its absolute last breath of physical energy to trip a tiny switch. And tripping that switch unleashes a brand new full-strength electrical pulse from the local battery down the next 50 miles of wire toward City C.
It is literally a relay race. It is a baton pass. The exhausted runner collapses, but hands the baton to a runner with fresh legs.
A baton pass is a perfect analogy. And if we want to connect this historical hardware to modern computing, this specific mechanism is where the telegraph diverges completely from the analog telephone networks that come later.
How so?
Consider an analog amplifier, like the ones used in early long-distance telephone lines. An analog amplifier takes the incoming continuous wave of a voice signal and just mathematically multiplies everything. It makes the signal bigger.
But the problem with analog, as anyone who has listened to a bad AM radio station knows, is that the wire picks up static, lightning interference, and magnetic noise along the journey.
Yes, so the analog amplifier multiplies the voice, but it also multiplies all the static noise the signal picked up along the way. You send that through 3 or 4 analog amplifiers, and eventually the voice is completely buried in a wall of deafening amplified static.
Because the amplifier is dumb. It cannot tell the difference between the human voice and the noise of a thunderstorm. It just boosts everything.
Exactly. But the telegraph relay is fundamentally different. It is a digital amplifier. It does not multiply the incoming signal, it regenerates it from scratch.
Because it's just a switch.
Because the relay is essentially just a binary switch. It is either tripped, closed by a pulse, or it is open. It completely ignores all the low-level static noise on the line. The static isn't strong enough to trip the switch. The relay strips away the distortion, the noise, the attenuation, and uses the fresh battery to create a crisp, perfectly square binary pulse.
It cleans the slate at every station.
It creates a mathematically perfect clone of the original signal. The relay is the world's first digital regenerator. This exact principle, using a small, weak electrical current to actuate a switch that controls a larger electrical current, is the foundational concept of George Boole's logical algebra.
Which is the basis of all computers.
It is the exact same concept that allows transistors in a modern microchip to perform logic. And it is the exact same principle used in fiber optic repeaters sitting on the ocean floor today, taking in weak light pulses and firing fresh lasers to the next continent.
It is genuinely mind-blowing to realize that the architectural foundation of modern internet routing and digital regeneration was completely solved with brass, iron, and glass jars of acid in the 1830s.
It's incredible.
But I think it is also deeply important to highlight, while reading these sources, the sheer brutal physical labor required to build this infrastructure.
The material reality of the network was staggering.
We use terms like the digital revolution or the cloud today, which sounds ethereal and weightless. But to build this 19th century network, humans had to physically conquer the landscape.
They had to chop down whole forests.
Right. They felled entire forests just to manufacture the millions of wooden poles required. They had to string thousands of miles of heavy iron and copper wire by hand across mountains and deserts. They had to scour the earth for better insulation materials.
Like gutta percha.
Yes, eventually discovering gutta percha, which is a natural latex rubber harvested from specific trees in Southeast Asia, just to coat the wires so the electrical current wouldn't ground out into the earth. Building a virtual space required an immense, brutal extraction of physical resources.
It was an industrial conquest of the natural world. But even as the physical network expanded globally, crossing borders, spanning continents, and eventually diving under the oceans, a new, unforeseen problem emerged.
Of course, there's another problem.
The physical hardware worked perfectly. The relays clicked, the batteries hummed, the poles stood strong. But the humans operating the network were running into massive compatibility and cognitive bottlenecks.
The network scaled faster than the software, essentially. Let's move to the human element. The sources describe a massive standardization crisis regarding the code itself as the lines got longer.
Yes. As the network scaled, especially across different climates and mediums, the original American Morse code, the code Alfred Vail optimized with his printing press analysis, began to show severe structural flaws.
Wait, I am stuck on this. We just established that Vail's character frequency analysis was a stroke of genius. It was the perfect .zip file. What could possibly be wrong with American Morse code?
Vail's analysis was brilliant for speed, but the structural design of the code had a fatal weakness when subjected to the harsh realities of long-distance physics. Some of the letters in American Morse code utilized internal spaces.
Internal spaces. Explain how that works.
For example, look at the American Morse code for the letter C. It was constructed as dot space dot dot.
Okay, so it had a gap of silence built directly into the middle of the letter itself, distinct from the space between letters.
Yes. And on short, clean overland lines, a highly skilled operator could hear that tiny internal space and distinguish it from the slightly longer space that separated two different letters.
But over long distances.
But as the network grew, and particularly when engineers started laying the first submarine cables beneath the oceans, physics threw a massive wrench into the system.
The sources mention that underwater cables cause something called smearing. I understand that gutta percha was used to waterproof the cables, but the text says the cables acted as massive electrical capacitors. Why does dropping a rubber-coated wire into the ocean suddenly turn it into a giant battery that ruins the code?
It is a fascinating quirk of physics. A capacitor, in its simplest form, is just two electrical conductors separated by an insulator, a dielectric. When you lay a telegraph cable across the floor of the Atlantic Ocean, you've accidentally built a capacitor hundreds of miles long. The copper wire carrying the signal is the first conductor. The salty, highly conductive seawater surrounding the cable is the second conductor. And the gutta percha rubber, wrapping the wire, is the insulator sandwiched between them.
Oh, I see. The ocean itself becomes part of the electrical circuit's environment.
Precisely. Because it is acting as a capacitor, the cable wants to store electrical charge. When the operator hits the key and sends a crisp, sharp, square pulse of electricity into the cable absorbs some of that energy, storing it up.
Okay.
And when the pulse ends, the cable slowly releases that stored energy back into the wire.
So the signal doesn't just stop instantly when the key is lifted, it trails off.
It bleeds. The sharp, discrete pulses of electricity entering the cable come out the other end, stretched, elongated, and distorted. That is the smearing effect.
And what does that do to the code?
When a signal smears, those tiny, delicate internal spaces inside letters like the American C just fill in with stray, lingering current. The silence is overwritten by the ghost of the previous dot. The letter becomes completely unreadable to the operator on the other side of the ocean.
The physics of the ocean was literally blurring the language. How did they resolve this? Did they have to invent better cables?
They eventually improved the cables, but the immediate fix was a software patch, so to speak. Enter Friedrich Clemens Gerke.
Who was he?
He's a German writer and inspector of telegraphs. In 1848, he looked at Morse and Vail's alphabet and aggressively simplified it. He completely eliminated all the space letters.
All of them?
All of them. In Gerke's revised system, every single character was a continuous, unbroken string of dots and dashes with no internal gaps.
So how did he fix the letter C?
The fragile American C, which again was dot, space, dot, dot, was replaced by a much more robust rhythmic sequence. Dash, dot, dash, dot.
That is much harder to smear together. Even if the cable blurs it, you can still feel the heavy rhythm of the dashes.
It was vastly superior for long-distance, electrically noisy lines. It was so reliable that it was officially adopted by an international congress in 1865 as International Morse Code.
Okay, so they fixed the bug.
Right. This standard was the linguistic bridge that allowed global interoperability. But as fascinating as the evolution of the code was, the most profound evolution detailed in these chronicles is what happened to the human brain.
Yes. Let's talk about the operators, because this section of the text is just wild. The sources talk about a massive cognitive shift in how the humans interacted with the machines.
They had to adapt to the speed of the network.
Right. Originally, the receiver had that stylus that embossed the dots and dashes onto the moving strip of paper tape. The operator's job was to take the tape, read the physical marks with their eyes, and transcribe it into English letters.
That was Morse's original design, and he insisted on it because he wanted a permanent physical record of every message, like a receipt.
But the operators quickly realized that reading the paper tape was visually taxing and incredibly slow.
Yeah, and they noticed something else. The electromagnet, pulling the heavy metal armature down, made a very distinct acoustic sound.
The clicking.
Right. It made a sharp, heavy clack when the armature hit the metal stop on the way down, and a lighter, springy click when it was pulled back up against the upper stop.
The duration between the clack and the click was the dot or the dash.
Exactly. The operators realized they didn't need to look at the paper. They just started listening to the machine. They trained their brains to translate those raw audio pulses directly into words in real time.
They bypassed the visual medium entirely. They just absorbed the data acoustically.
They completely stopped looking at the paper. In fact, many operators found the noise of the paper unspooling distracting and would purposefully remove it.
That's amazing.
This represents a profound cognitive evolution. The human operators essentially became biological data processors. To handle the incredible speed of the incoming messages, they had to perform what computer scientists now call real-time mental buffering.
Mental buffering. I want you, the listener, to really imagine what this takes. Imagine you are sitting in a telegraph office, listening to a relentless hail of acoustic clicks and clacks. You have to translate that rhythm into letters, assemble those letters into words, and then write those words down with a dip pen on a telegram form.
But you cannot physically write with a pen as fast as the machine is clicking. It is impossible.
So the operators would hold several words in their short-term memory, buffering the data while their hand wrote down the previous sentence, all while their ear was actively taking in a completely new incoming audio stream.
It is biological RAM.
It is like doing simultaneous translation at the United Nations, but you were translating pure rhythm into text while constantly lagging behind the audio.
The cognitive load is staggering. And because these operators were essentially acting as human routers managing the flow of global traffic, they quickly realized they couldn't just send raw text.
Right. If you just blast data into a network, it descends into chaos.
They had to invent network protocols to manage the flow of information.
They needed metadata. The sources mention a few of these manual protocols, and they map perfectly onto modern computing. For example, they invented collated messages.
Yes. If a bank was sending highly sensitive data, like a massive financial transfer, or a government was sending a military order, you couldn't risk a single letter being dropped by a faulty relay.
The stakes are too high.
So you would request a collated message. This meant the receiving operator was legally required to telegraph the entire completed message back to the sender so the original sender could verify it character by character.
It is a manual loopback handshake. They are literally doing a checksum to verify data accuracy.
It doubled the time on the wire and doubled the cost to the customer, but it ensured absolute fidelity. They also invented the concept of the preamble.
What was in the preamble?
Before the actual body of the message was sent, the operator would send a highly standardized header of metadata. It included the sequence number of the message, the originating station's unique ID code, the time it was sent, and critically, the word count.
So if the header says word count 25, and the receiving operator buffers the message and only writes down 24 words, they instantly know a data packet dropped. They know there was a transmission error somewhere on the physical line.
And upon realizing the discrepancy, they would immediately halt the sender, reference the sequence number, and request a retransmission of the missing segment.
And to do this quickly over the wire without wasting time spelling out, please repeat the last sentence, they developed Q codes.
The Q codes are brilliant. They are three-letter abbreviations to manage the actual state of the network.
You need some examples.
Well, QRL meant, I am busy, do not interfere with this transmission. QRN meant, I am troubled by static noise, please send slower. QSL meant, I acknowledge receipt of the message.
I am reading this section of the Chronicles and thinking, these operators were manually doing the exact job of a modern internet router and TCP/IP protocols. Packet headers, checksums, flow control, error requests. It was all being done in real time by guys in wool waistcoats listening to the clicking of iron magnets.
It is the exact same logical architecture that governs the modern internet. The rules of data routing do not change, only the substrate changes. In the 1850s, that architecture was executed by human cognition instead of silicon microprocessors.
We have covered an astonishing amount of ground today. Let's recap this journey through the sources. We started with Luigi Galvani making dead frog legs twitch, treating electricity as a biological parlor trick.
Right.
We saw Alessandro Volta tame that energy into a continuous river with the first battery in 1800. We looked at Ørsted's serendipitous compass twitch in a Danish classroom and Sturgeon's electromagnet, which finally gave humanity a controllable binary force at a distance.
The ones and zeros.
We saw how Morse and Vail threw out the complex, fragile five-needle dials of the British in favor of the single wire, using statistical analysis at a printing press to invent a mathematical digital code.
And we covered the digital relay.
Yes, the brilliant invention of the digital relay to defeat the physical resistance of the wire, regenerating signals so they could span continents. And finally, we looked at how operators evolved into acoustic, biological routers, dealing with submarine capacitance and inventing the very network protocols that manage our data today.
It is a remarkable century-long trajectory, from a parlor trick to global nervous system. But if I can leave you, the listener, with a final provocative thought to mull over based on these texts, it's this. The telegraph didn't just change technology.
What'd it do?
It didn't just lay the physical groundwork for the internet. It fundamentally rewired human culture and human psychology.
Build on that. How did it rewire culture?
Consider the way we write. Because sending words over a telegraph wire was incredibly expensive. You paid by the letter, and the line could fail at any moment. It completely killed the flowery, verbose, romantic writing style of the 19th century.
Oh, wow.
It birthed the concise, punchy, inverted pyramid style of modern journalism. Reporters were forced to put the most vital facts, who, what, when, where, in the very first sentence, just in case the wire went dead before paragraph 2. The telegraph structurally changed the English language.
That makes perfect sense. The medium dictated the message.
Furthermore, consider time itself. Before the telegraph, every single town ran on its own local sundial time. Noon was simply whenever the sun was highest in your specific town. If it was 12 o'clock in Washington, it might be 12 to 12 in New York.
That sounds chaotic.
It was fine before instant communication. But you cannot run a continent-spanning time-sensitive digital network, coordinating train schedules and financial markets, on thousands of different local clocks. The telegraph literally forced the world to abandon local solar time and adopt synchronized time zones just to keep the network's data packets aligned.
It standardized human time.
It standardized time. It created the concept of the 24-hour news cycle, and it created the expectation of immediate global updates. And with that expectation came the first waves of real-time anxiety.
The doom scrolling of the Victorian era.
Exactly.
Yeah?
Long before humanity wired the globe with fiber optics, long before the smartphone, the telegraph was actively rewiring the human mind, conditioning us for the modern age of instant gratification and constant connection.
So, the next time you feel overwhelmed by the constant buzz of your smartphone or the endless scroll of a news feed, remember the frog legs, the compass needles, and the acoustic operators buffering Morse code in their heads. The infrastructure of our anxiety is almost 200 years old. Keep questioning the infrastructure hidden in plain sight. Thanks for taking this deep dive with us.